Exercise 2. Let's go. It's question number 1. PG is the normal to the centered ellipse at PG being okay. GP is produced outwards to Q, so that PQ, okay. So that is locus of Q. Oh wait, what? PQ is equal to GP, huh? That's weird. So that the locus of Q is an ellipse, so it is this thing, and find the equation. Okay, cool. So we obviously know what the point P is. It's just a cosine theta comma B sine theta. And yeah, okay. So that the locus of Q is an ellipse. Fine. And what is this G? So it's the intersection of normal with the x-axis. So you got x cosine theta upon A minus y sine theta upon B is equal to A squared E squared, right? Yeah, that's the same, of course. So whenever y is 0, x intercept just becomes like, oh, wait, is this correct? No, it's supposed to be x A upon cosine theta. And then y b upon sine theta, right? So whenever y is 0, x just becomes a E squared and then times c, right? Oh yeah, sure. So it just becomes a E squared c. Is that right? Yeah, it must be a squared minus b squared, like that. That's a squared E squared, right? And this should work. Okay, comma 0. So that's what G is going to be. And then we just want Q, which is, so you just have P being the midpoint of G and that, right? So basically what that means is like 2P is equal to G plus Q. That is, Q is just equal to 2P minus G, right? I guess. So that would just be, so 2AC minus AE squared C and then comma 0. That should do it. Right. Oh, sorry, comma B times sine, okay, 2 times of that, right? So 2B sine, as you can see, this thing is like something, so 2A minus AE squared something times cosine theta, and then once again something times sine theta. So yeah, it's an ellipse, and eccentricity, well, 1 minus E squared, call this capital E squared, that's going to be equal to so this thing and this, oh yeah, square of that, in fact. So it's supposed to be 4B squared, and this thing upon this guy square is just A square, and then you got 4 minus, oh, you just want like A square plus B square, then fine, okay, then it's gonna be slightly different, well, okay, I'm still gonna go with E square and stuff, fine. So you got, think about it, it's like 1 upon A, and then you got 2A square minus A square E square, but A square is just like some negative of that. That's gonna be B square minus A squared, right? So A square minus B square is A square E square, but negative of that is plus B square minus A square. So it's really just, A square plus B square, well, 1 upon A of that. Right, but we want this to be squared actually. So there we go. And that's gonna be equal to 4 A square B square upon A square plus B square square, which is like A power 4 plus, okay, that's 1 minus E square, so like E square has to be 1 minus this guy. So this, yeah, it's going to be A square minus B square square upon A square plus B square square. So just take the square root, and if A is bigger than B, then this must be the thing. It's cool. Right. And find the equation of locus of intersection of the tangents. Right, so this thing is done. And also finding this equation of the locus of intersection of tangents at P and Q. What? At P and Q. But like Q, wait, what? Okay, I don't get it. But Q is just a random, I mean, like tangent at Q to what? To the new ellipse, I think. I guess. Yeah, to the new ellipse, right? Okay, and you want the locus of intersection of these tangents. Oh, not liking it. It's too much. Don't you think it's just too much? Yeah, right. Okay, just keep on going. We have to figure out the equation now. Okay, I hate this. So it's gonna be like x squared upon, or yeah, okay, x cosine theta upon a. So that's gonna be like x c upon this quantity 2a minus a e squared, and then plus y sine theta upon this quantity, right? I think that's how it's supposed to be. Okay, so hope that that's right. Oh god. Yeah, hopefully that's right. Okay, upon 2b equal to 1, that's the tangent. And by the way, this theta and that theta is, both are in fact the same thing. Okay, and then this guy just is like x cosine theta upon a plus y sine theta upon b is equal to 1. So we want to find locus of intersection of the tangents at p and q. Now I'm thinking of something. Isn't it like saying that cosine theta times this vector, or you might as well just say like x cosine theta times, no, okay, x is a variable, right? Uh, okay, this is weird. Okay, it does mean that actually. So, but there's no three equations or anything like that. It's, it's very weird actually. So whatever point we have, it must follow like both of these equations. Okay, understandable. So I just want to get rid of theta somehow, right? Hmm. I want to get rid of theta somehow. Well, one thing we can do is just multiply this by 2, and then you get this thing, and then subtract, and you get x, and from there you get y. It's just painful. But what other choice do we have? Just keep on going. Hopefully we'll get something nice. So x cosine theta, and then you got 2 upon 2a minus ae squared, and then that minus of this, so minus of 1 upon a, that's equal to 1. So x cosine theta times, oh god, yeah, not really helpful. Are we sure this is correct? I mean, it's an ellipse. It's another ellipse, right? No, we just want to find the locus. We don't know if it's ellipse or not. Maybe some kind of like hyperbola. I don't know. I don't know. Doesn't look good, right? Yeah, doesn't look good. That these guys do. Come on, think. What can we do about it? How do we think about it? Like what's happening exactly? Solving this whole system and then figuring out x and y. That's just, yeah, I don't like that. I really don't. What about x upon, so like 2x upon of, and then that might have, this is like cosine theta and sine theta and something. And x and y. So cosine theta and sine theta vary, right? That's the thing. And then coplanarity with 2 vector. I mean that's like obvious, right? 1 comma 1 or something. One, think about it. How would you do it? It's like you got 2 random vectors. No, it's not supposed to be just 2 of these, is it? There's no third vector, but that's obvious, isn't it? Like everything it has to be 0. I get that. Right, just do it. Hopefully something nice will happen. Okay. So it's gonna be like 2a minus, okay, that's canceling out, just a squared, and that upon a times of 2a minus a, sorry, it should be a squared, not a squared e. Right, a squared, and it's supposed to be a squared as well, equal to 1. This cancels. Just got x cosine theta is equal to a times of 2 minus e squared, and that thing upon e squared, understandable. Okay. And then similarly you can like solve for y sine theta. Okay, and then this, put that in here. So it's supposed to be y sine theta upon b is equal to 1 minus of, so 2 minus e square upon e square or something. Yeah, which will be like 2e square minus 2 upon e square, which is basically just e square minus 1 upon e square. So there we go. You got y sine theta is just equal to b times of this stuff. E square minus, okay. Not nice. And then you're gonna divide by x and divide by y, and then square and add. Just get 1 is equal to a square. Okay, just take that 1 upon e square common, like 1 upon e power 4, sorry, that common. Then you got a square 2 minus e square squared upon x squared, plus that's out, it's supposed to be b square, and then e square minus 1 squared upon, oh, it should be y over there, sorry, upon y squared. I don't like this. I can take a inside. It's gonna be like a times a plus. Okay, no, just no. That will be painful. Okay, just leave it like that instead. Whatever this is, most likely I made some kind of mistake, or if I didn't, that is actually the answer. And not very good looking. Next, second question. PQ are the corresponding points on a standard ellipse and its auxiliary circle. Corresponding points on the standard ellipse and its auxiliary circle. Oh, okay, so like it shifts to that. The tangent at P to the ellipse meets the major axis in P. Okay, just draw it out. P is just some point over here, and then this is the auxiliary circle. We got Q as this point right above it. Tangent at P meets the major axis in capital T. Okay, it's gonna meet at capital T, whatever. Prove that QT touches the auxiliary circle. So that is basically like this. Okay, fine. The point of contact from here to here is touching at Q. Why? Why is that the case? Seriously, that's like saying that from here to here, so that slope is perpendicular to that slope. We'll see what we get. This is supposed to be just a cosine theta comma a sine theta, and this is supposed to be a cosine theta comma b sine theta and whatever. This tangent intersection point, right? It's supposed to be a upon cosine theta, and then 0. Okay, so this whole slope, that's a sine theta upon, it should be, no, it's not supposed to be or anything, and then a times cosine theta minus 1 upon cosine theta. Yeah, it cancels. Cool. So s upon, well, c squared is 1. Is that right? It must be, right? Yeah, sure. It's gonna be negative, and then you got s squared. This c comes on the top. Yes, negative. This cancels, like negative c upon s is this thing, and then this, of course, is just s upon c. That's the slope. So there we go. The multiplication is -1. Sure, it touches it. So second, done. Next question. Third, the point P on the ellipse is joined to the ends a dash of the major axis. Joined to the ends a dash of the major axis. Okay. If the lines through, just draw it out actually. So point P, this is a dash, right? If the lines to the P through P perpendicular to PA and PA dash, okay, so like this, fine. They meet the major axis in Q and R, then prove that length of QR is length of lattice rectum. Oh God. Length of QR is, what is this? Wow, amazing. How do I get that? How get that length? So that's a 90-degree right there, isn't it? Sure. Maybe you can figure out this length. No, that length is just too much to figure out. You do know what this is, at least, right? And then you kind of also know what the tan of this angle is, right? Maybe it isn't that hard. So theta, let's call this letter as L. Then this is going to be L tan theta. We can figure out what L is later, and also theta, what is that later. We actually already know what this thing is. So it's, yeah, okay. Doing that is the same thing as trying to find out what this thing is. Fine. So once you find that, after that, what you have to do is like multiply by, so sine theta, right? So this length times sine theta. But wait, what? No, sorry, this length times tan theta, that will give us this thing. Isn't that what we want? No, No, wait, what do we exactly want? We want, uh, wait, I don't, wait, what do we want exactly? I guess we just want this length, right? Or this length. I mean, figuring out this length is good enough, I think. I think. Wait, okay, something's not going correct. We do want this length, right? Yeah, so you already know what the coordinate of this thing is. If you figure out this length, you are done basically. So that's like dividing this thing by cosine theta. Hmm, nice. But then this thing is, how do we get that? It's like this length divided by cosine theta, and then you're dividing that by cosine theta. So this is L upon cosine square theta, basically, right? Yeah. But what's cosine? It's like 1 plus tan square theta, and tan square theta is like much easier to deal with. So tan square theta, sure. Right, I think this is doable. That's going to be this length, right? Okay. And similarly, you will have something from here. So this is like L upon 1 plus m squared. Of course, that's what this whole thing is. Isn't that right? Huh? I guess, yeah, it must be. Okay, just review what we did. This whole length we can figure out by, let's say it's L. Then to get this length, we will do L upon cosine theta, right? And then we from here we want to get this length, so that we do L upon cosine theta upon cosine theta, which is L upon cosine square theta. That's going to be 1 upon 1 plus m squared right there. Yeah, sure. Shit, no. That's wrong. That's wrong. It's L secant square theta, right? So that's going to be L times of 1 plus m squared. Yeah, that's more like it. Okay, so you will figure out this length through that. And L is not that hard, and 1 plus m squared is also actually not that hard. Right, so let's figure it out for this point. So this point is, of course, a cosine theta, comma b sine theta. This point is negative a comma 0. The slope, that's supposed to be b sine theta upon, so the difference, which is a times of 1 plus cosine theta. Right, and then you want to square that. So, wow, okay, maybe we should use something else. This can be written as b tan of theta upon b upon a tan of theta upon 2, right? Call this whole thing as t for now. It's going to be b upon a times t. That's our m. So L, and then you got 1 plus b square upon a square times t square. Sure, that should work. Okay, that's nice. That's this. Oh, and by the way, L is just, L is just, difference between these two, which is a times of 1 plus. Hey, why didn't we do that right away? We should have done that, right? Exactly. So if we did that right like that, so it's gonna be just, a times of 1 plus cosine theta, and then 1 plus m squared is this thing, b squared upon a squared, and then sine square theta upon 1 plus cosine square theta. Sorry, cosine theta squared, right? Wait, isn't that just like 1 plus cosine theta times 1 minus sine theta? So like that's basically 1 minus 1 minus cosine theta upon 1 plus cosine theta. Yeah, and then when you do this thing, it's going to be a times of 1 plus cosine theta plus b squared upon a times 1 minus cosine theta. Cool. That's the that's this thing. What we actually want is negative a plus this, right? That's going to be the x coordinate. Nice. Sure. So negative a plus a times of, at this point just put it as ac. So ac plus b squared upon b squared upon a, and then you got 1 minus c. There we go. You got this coordinate. Similarly, you just want to figure out what this coordinate is, right? So pretty much the same stuff, except that instead of a, let's just put negative. No, that's not nice. It's supposed to be a. Okay, just do it the usual way. M would just be b sine theta upon n magnitude of m basically. Then you got 1 minus c squared. It's only 1 plus c upon 1 minus c right there. And then this is going to be equal to 1 minus c, right? Because we want this distance. Sure. And then doing the same thing, you squared 1 minus c right here, and then 1 plus c right here. And then a plus this guy. Wait, plus or what? No, okay, we want a minus this guy actually. Right. So that's going to give us, a cosine theta minus b square upon a, and then you got 1 plus cosine theta, right? Yeah, that's the thing. That's what this thing is. Okay, and then you're just going to do this thing minus that thing. So this cancels. And then it's going to be b square upon a and 2. There we go. So 2b square upon a, that's equal to the spectrum length. That's it. That's all we had to do. Next question. Third is done. Fourth. Let S and S dash be the foci. SL, the semi-lattice rectum of this ellipse, and SL dash produced cuts the ellipse at P. S dash are the foci. SL be the semi-lattice rectum of the ellipse. Okay, that's b square upon a. And S. Oh, okay. So actually, it's like this thing. Fine. That's L. Fine. And LS dash, so this thing, produced cut the ellipse at P. So this thing, right? Okay, weird. Show that the length of the ordinate of P. So this thing is just 1 minus e squared upon, okay, fine. Where 2a is the length. I think this is geometry bit, by the way. Okay. Length of the major axis and e is the eccentricity of the ellipse. Right. Can't be that hard, can it be? Yeah, sure. Okay, just gotta. What about this point? Huh? So 2a or something? Nah, that's too much. Probably not worth doing. We need to figure out what this must be to actually get this right. Yeah, okay. The x value of that thing or something like that. That's bad. Maybe just figuring out what this theta is actually good for us, because then we can use, oh yeah, why not just use the other parameterization that I always use, and then from there you can figure out directly what p should be, taking s dash as the center, sorry, the origin. Once you have that, you just need to figure out what the y coordinate is, right? And then you're done basically. Okay, so this angle, we'll call this thing as theta or something. So tan theta is, this is 2b square upon a, and that's just equal to 2ae. And what's this length? I don't know. Tan theta is just this thing upon that. It's supposed to be base. Oh, it's supposed to be b square upon a only, right? Not gonna make that mistake once again. B square upon 2a square e, right? Sure. That's what tan theta is. Which is of course just 1 minus e square upon 2e. Okay. And what we just want is this y coordinate. Cool. We know that this guy will just have the coordinates as, so e power I theta, and then, oh, by the way, the system length is, yeah, like a is just b square upon a, right? Sure. And then this upon 1 minus e cosine theta. Oh, by the way, theta is not what we'll use. Instead, we'll use the complete thing, which is theta plus pi. So instead, it will be an e power I pi, that's -1. This thing. And it's going to be 1 plus cosine theta. Cool. And we just want the y coordinate, of course, right? There we go. What's the y coordinate going to be? It's going to be negative b squared upon a, and then got sine theta upon 1 plus cosine theta, which, ooh, I just want this. You know what tan theta is, but you don't know anything more than that. That's unfortunate. Okay. It's gonna have all this weird stuff. That's not what I want. No. Oh, sorry, it should be this times the eccentricity. Why did I forget that? Okay. So eccentricity times all of this. And this E and this E is different. This is for the eccentricity. This is for the Euler number. You get the idea. Just do 1 plus E cosine theta. Interesting. We just want the length anyway, so this is what we want. Now, sine theta upon 1 plus E cosine theta, that's what we look for. But how do we get it though? Tan theta is this thing. Oh god. So we like b square upon a, and that upon, so cosec theta plus e cot theta. So cot theta is not a big deal. It's just this rule of this guy. Cosec theta is a big deal, unfortunately. I think tan theta is like 1 minus e squared, and then you got 2e, and what's this going to be? Square root of 4e squared plus 1 minus 2e squared plus e power 4. This cancels plus, so it's going to be 1 plus e squared, right? Okay, there we go. That should do it. Or okay, let's just not do that. Instead, just directly use this thing. So e squared upon a. For sine theta, I'm just gonna do this 1 minus e squared, and then hypotenuse I'm gonna put here. So 1 plus e squared, and then you got plus e times of cosine theta, which is just, it just has 2e as the adjacent, and that's why, yeah. B squared upon a, that is like a times of 1 minus e squared, so 1 minus e squared squared. Yeah, wait, what? Why is that squared? Is that correct? Seems like it's correct. It was really a times 1 minus e squared, isn't it? Sure. That was the thing, of course. We know that. Then it has to be like this. Did I mess up anywhere? No, it doesn't look like that. So they are like, okay, yeah, and that is just squared over there. Okay, and this is 1 plus e squared plus 2e squared is like 1 plus 3e squared. So the length of ordinate is this, not that. Huh. Where did extra thing come from? Did I make this wrong somehow? No, no, that's correct. It's correct, man. Right? Yeah, it's correct. Of course, of course. Oof. Okay. Yeah, 2b square upon, right. Okay, b square upon a, and then upon this guy, it's going to be this thing. Yes, it's correct. That's right. They missed a square over here. It's supposed to be a square. Right. So it's 1 minus e square upon 1 plus 3e square times a. That's more like it. Next. So like, for example, what about a circle? For a circle, eccentricity is 0. So this will like, okay. Yeah, it's going to cancel out and just get like a would be the thing. So for a circle, you know, because e is 0, this is like both of the foci in fact, and the lattice rectangle, that is just the radius. And you have, and wait, what was p once again? Right, okay, the other guy that's produced, so it's gonna be just this line once again. It's gonna cut over here, basically. The ordinate of this thing is, of course, is a. Makes sense, right? That's how, okay, that's in here as well. So looks like both of these are correct. Now, of course, cannot be. It must be just this thing, right? It has to be that thing. Can't be anything else. Sure. Sure. Yeah. Anyway, next question. Fifth. A tangent to the ellipse touches the point at the point P on it in the first quadrant. Tangent to this ellipse. It's supposed to be an ellipse, not a circle. Okay, this is just, yeah, this is better. Tangent at this thing touches up at the point P. It's tangent at P basically. What about that? In the first quadrant, fine, and meets the coordinate axis in A and B. Okay. If P divides AB in ratio 3:1, so this thing is 3, this thing is 1. Okay, understandable. Find the equation of the tangent. Nice. You know what I'm thinking? Just, you know, to figure out the eccentric angle, just do a reverse transform and then make this a circle, because the ratio will still remain the same, right? Yeah. So now you just got to figure out what angle is such that, you know, this is cut in ratio 3:1, right? So you got this as theta, and right, this is 1:3, of course. So this thing, it's like that's 1. Okay, not 1, it's a, but you get the thing. So this thing would just be a tan theta. So tan theta is to What about this guy? It's tan of this angle, which is cot theta right there. That has to be equal to 3, right? Which is tan square theta equal to 3. So like tan theta has to be square root 3. That means theta has to be 60 degrees. That's it. That's all you really need, because now you have the centric angle. You're good to go. Cool. Okay, and we just want equation of the tangent, right? So now that we have the theta, good to go. X upon a, and then cosine theta is just square root, no, sorry, 1 upon 2, and then plus y upon b sine theta is just square root 3 upon 2 is equal to 1, right? That's it. That's the tangent. So yeah, just gonna put that as an answer. X upon 2a plus square root 3y upon 2a is equal to 1. Sorry, 2b, right? Next, sixth question. PCP dash is a diameter of the ellipse. Okay, so some ellipse, it's a diameter of that is passing to the center. What about it? A is bigger than B, and QCQ dash is the corresponding diameter of the auxiliary circle. Oh, so if you like shift these up, fine. Show that the area of parallelogram formed by the tangents at. Oh no. So central angle of the point B formed by the tangents, huh? I just hate this. Oh god. How do I even respond to this thing? Okay, you can figure out these tangents and something. Okay, you can like figure out the length between the tangents, I guess. Uh, and okay, the other guys. Oh, those are just like 90 degree or something. Fine. Huh. Anyone else feel that's not good? Come on, think about it. Think about it. So you just have to draw it out first of all. That's not an ellipse. That's better. Just cancel all that. Auxiliary circle and whatever. This is the center. You will have these as things. Okay, so no, okay, it's supposed to be PP dash over here, and then this is not supposed to go that big. Just this much should be okay. Actually, no, you know what? Let it be. Nah. Instead, we will make this shorter. Okay, and the corresponding points are over here. So this guy. Okay, nice. Hey, you know what? Okay, wait a second. You know what these vectors are, right? So just the cross product of those vectors, right? Okay, this is supposed to be interesting. And the tangents at okay, the tangents at those points. That's what we are looking for. That makes everything more complicated. Even drawing a figure is just hard right now. Hey, wait, what happens if, say, these are like PP dash, these are like really near to this or something? Okay, fine. Eccentric angle is given. Then you have to figure this out. Sure. Okay, just keep on going. We'll see what we get. And then the same kind of tangent, the same slope. Okay, this is bad. It's looking really bad. Copy paste. Yeah, right. Okay, fine. And then the tangents of these guys, which is something like that. No, something like this. No. This is just okay. Now that didn't even become a line. Okay, just deal with it. How is it even making a parallelogram? Just shrink it, and copy. Like, how are these making parallelograms? We'll just extend these. Right, these are intersecting, and Yeah, sure, but these are like gonna intersect really, really away and not nice. Now what do we do? And wait, you know what the distance between these is, right? Okay, actually, you kind of also know what the side is supposed. No, no, you don't. You unfortunately don't, right? Just know the distances. That's all you know. Okay. Uh, Maybe you know the vectors or something. Sure. So you got some parallelogram. What do you know about this configuration? What do you know is the distance between these two, uh, right? And also what vector this will make, right? So yeah, like these two are, let's just say these two parallel sides, and then you got these other two parallel sides. So you know what vector these make. Sure, what angle these make. Uh, oh, we don't, unfortunately. Actually, this is not looking nice. You can't just we can't even draw out the figure. Actually, it's just too much, right? Yeah, it's just too much. Think, think. You just know the distances between these. Okay, that's one thing we know. We want height times base. What would be our base in this case? We don't know. We can't just figure out the intersection points. That would be just too much, right? Hey, so going from here to here, okay, you can figure that vector out. So going from there to the, that's not important. Okay, what you need is this vector, right? Yeah, sure. That's interesting. Oh yeah, so you can actually figure out this vector as well as this vector actually, right? Cool. Or this. No, you can't figure that vector out unfortunately because the length of that vector is not defined till now. And now with just these vectors, can you actually get the right, can you get the area of algebra just with these two vectors? I don't know. Is it even doable? Just these two vectors, and you want to get the area. With these two vectors, it would be really nice. You just take a cross product and you're done. But when these are not, then it's hard, isn't it? Yeah, it's hard. Wait, aren't these like just these vectors but rotated by 90 degrees? Oh wait, look, wait a second. Yeah, I mean these are just these vectors. So here to here, like this thing, but rotated, right? Interesting, interesting. But yeah, its length also changed. So that's another thing we have to look for. It's gonna take forever like this. If we can't just take a cross product, then it's not gonna work. Just given the lengths and the directions, can you actually figure out the thing? No, no, you can't. It's not easy. You can figure out this angle, whatever. From there, you can figure out this angle. Sure. Okay, if these are like L1, L2, then and call this angle as theta, then what you have is like L2. Now this is angle showing 90 degrees theta, right? So L2 secant of L2 upon sine theta, right? Okay, that's gonna be this length, and that times of L1. This should give us the area, sure. But we don't know what sine theta is yet. So instead, what we'll do is like L2 L1 upon. So to figure out sine theta, just do L1 cross L2 and then divide by L1 L2, right? Make a magnet of that, of course. So division by that. Okay, it's like this thing. Ooh, that's nice. I guess it's doable after all. Let's do it. Huh. I mean, I didn't like it like that because I had to do this. If it was more geometric, it would be even better. But this is also fine. We can deal with it. Okay, so now the thing is, so you got this diagram, you got this circle. Yeah, fine. Don't even do that. Don't even do that. Just figure out the perpendicular from there to there, right? Yeah, it's gonna work. And also what the direction of that thing is. Yeah, I guess that's how it's supposed to be. Uh-huh. So hey, you know what q dash is, right? What that vector? So it makes angle theta, and then of course L one vector. So going like q dash basically, right? That's going to be equal to 2 times r, which is just a in this case, and then along the direction, which is so it makes theta is supposed to be cosine theta comma phi, cosine phi, and then times sine phi, right? Yeah, that makes sense. Okay, that's nice. Uh, that's L1 vector. What about L2 vector? So L2 vector is, I mean, it's the same thing. It's Q dash, but then deformed basically, right? So the y coordinate is now changed to b. So of yeah, okay, that makes sense. L2 vector is supposed to be 2 times a cosine phi comma b sine phi, right? No, no, that's not perpendicular, right? That's not the perpendicular. That's just the right. That's not even gonna make it. No, it's not going to make it, unfortunately. Huh? It's not even a side, basically. So there's no use for this actually. We just want the perpendicular, right? Ah, not nice. What does the tangent make? So what is the vector along the tangent, or the yeah, that's supposed to be like negative cot theta, isn't it? Sorry, cot phi. Now this will become negative cot phi times b upon a, of course, because y changed by b delta y became b delta y, sorry, b upon a delta y, and that's why this thing. Okay, so that will be the slope of the tangent, I guess, right? In the morph, that is the ellipse thing, right? So for the normal or whatever, you just want negative one upon this thing. That's what we tan phi times a upon b, right? Sure. So it makes this vector with okay, understandable, fine. And the tangent's equation is of course like x cosine theta. Hey, okay, do you have to do that like that? Makes this angle. It's taking forever. Right? It's taking forever now. Fine, let's just do this. So then the tangent would be like x cosine phi upon a plus y sine phi upon b is equal to 1. So the length between those would just be 2 upon square root of cosine squared phi upon a squared plus sine squared phi upon b squared. So, right. Okay, it's already looking really problematic. I don't know. Is it even worth doing? Maybe it's not. Because this length, oh, it's just horrible. And then after this is done, you want to multiply this length by the unit vector, making this as the tan of the angle, right? That's just too much of work, isn't it? Uh, so what will that unit vector look like? It's a cosine, so a sine over here, and then b cosine over here. So the square root of a sine square, a square sine square plus b square cosine square. So then the unit vector would just be a sine comma b cosine upon square root of a square sine square plus b square cosine square. Good thing is like that cancels out. Okay, you're gonna have square roots. Not good, man. Just not good. It's gonna take forever. 2a sine comma b cosine. Uh, that's also like b cosine. Okay, this that thing, but that comes out. So ab on top. It's got a square sine square plus b square cosine square. Right. This vector is L2 vector. Crazy, isn't it? Yeah. This is not nice. Something else. Something else. Not this. Just not that. Mhm. Nope. Gotta deal with it. Fine. So L1 cross. It's already taking my soul now. I think 4a squared and whatnot. Oh god. Is this even worth it? Right? Is this even worth it? This thing is more like L1, L2, the magnitudes, just that, and then L1 hat, L2 hat. Okay, the magnitudes of those are like gone in any case. So upon L1 hat cross L2 hat, something like that, right? Sure. So the magnitudes of these guys, what would that be? We've got A square, B square. Oh god. Yeah, that's supposed to be just sort of that thing. Okay, cool. So the magnitudes are just 2a and that times of uh 2ab upon square root of a square sine square plus b square cosine square. Okay, that's the magnitude part, and then you gotta divide by L1 cross L2, right? So L1 times L2. Oh, sorry, the unit vectors, just those. So okay, no need for all of this then. Just look for cosine phi, sine phi. Right, that's one vector. And another vector would just be, a sine phi, b cosine phi, and that thing upon square root of a square plus b square. Sorry, a square sine square plus b square cosine square, right? You gotta divide by the cross of these guys. So look, this will cancel out. So you gotta divide by this. Sure. This will cancel out. Perfect. It's got 4a square b square upon, oops, 4 square b, just that much. Upon this whole thing, right? It's gonna take forever. So you got to have this thing. Yeah, it's looking good. You already got a square b, and maybe you will get this as well. Maybe. Did I make that 2 times or not? Because oh, maybe I didn't. No, I did. I definitely did, right? Yeah, it has to be. Right. There you go. Okay, cool. So the cross product of these guys, huh? Let's look at it. Cosine. Yes, okay. Cosine sine, and then cross a sine, b cosine. This times that's like b c square, and then minus a square sine square. That's all it is, right? Yeah. Sure. And then that should be written as this. Why? I don't get it. No, I don't. I don't get it. Why are you writing like that? How it's supposed to be AC just like that? No, why should that be the case? Why is it supposed to be? Oh, okay, sorry. It's wait, it's supposed to be cross, of course, right? Because sine theta. Then I switch that. Then it's got c squared over there. How did I switch that up? Shit. Shit. Did I do that correctly or not? Oh, okay. Maybe I messed up. I messed up. The thing was a upon b, and then yeah, you had to do that thing. Tan phi. That's the vector that normal would make, right? So it's supposed to be sine. Sorry, a sine, and then upon b cosine. So first b cosine should be there, and then a sine. Okay, so just the order is different. Other than that, everything is correct. So yeah, it's supposed to be b cosine and then a sine, and then it would be correct. So just for this much, I've done so much of problematic things. Okay, it's supposed to be ASC minus BSC. That's why this thing. So just multiply by 2 on both sides, you get this. Cool. Finally, it's done. Next question. I thought vector analysis would like make this better. It just made it worse. 6th is done. 7th. If the normal at point P to the ellipse intersect it again at point Q, show that cosine theta is equal to negative 2/3. Oh, it's 2 theta, huh? Weird. Okay, no big deal. So normal at P intersect it again at this guy. Okay, fine. What's the normal? It's supposed to be X. I'll just not use this right now. I'm gonna use the general form instead. So xa upon cosine theta minus yb upon sine theta. Let's say this is alpha, so sine alpha b, and then that will be beta or something. That's equal to 1. Oops, sorry. A squared minus b squared. Yeah. And then we are saying that a cosine beta and b sine beta is the point that lies on this. So that is going to be like a square cosine beta upon cosine alpha minus b square sine beta upon sine alpha. That would be equal to a square minus b square, right? Okay, nice. And now what? Ooh, okay, so without actually some special angles, it's just not good. You won't get anything from it. You have to put like 2 theta or something like that. Otherwise, yeah, not solvable. You won't get a nice relationship. Fine. So let's do it. Let's just put um let's just put alpha as theta and beta as 2 theta in this. It's supposed to be a square and then cosine 2 theta 2 c square minus 1. So this is gonna be 2c, so cosine theta, that is minus 1 upon cosine theta, and then minus b square. This whole thing is supposed to be 2 sine cosine theta upon sine theta. It's going to be minus 2b square c. That's equal to a square minus b square basically. And you just want everything in terms of eccentricity or something. Well, okay, I'm going to use a square minus b square throughout. So yeah, it's going to be, let's call this capital A and capital B instead. Okay, so capital A times 2c square minus 1 minus 2 capital B times c square is equal to capital A minus capital B times, so that cosine goes with, yeah, supposed to be c square times 2 capital A, then for the cosine, minus 2b, sorry. So basically 2 times of A minus B, c square, then you got minus A as the constant, and this is the, yeah, like plus A minus B times C, is that right? Must be right. And then minus A is equal to 0. I would think. Okay, cool. Right. And yeah, right. Okay. So this is like 2c square plus c minus a upon a minus b is equal to 0. Okay. How is this even helpful? Oh, you got this thing. Fine. No big deal. Keep on going. Let's see what we get. So now capital is just a square. It's gonna be a square minus b square. It's like a squared e squared right there. That's cancels. Just get 2c squared plus c minus 1 upon e square is equal to 0. Interesting. And now what? Yeah, we are stuck. Okay, you will have, at this point, you will have to put these in there. So let's do it. It's going to be 2c square plus c minus, what's capital A? Capital A is just 14, because, right? That's what this thing is. Of course, so minus 14 upon A minus B is just 14 minus 5, which is 9, equal to 0. There we go. So it's like 18c square plus 9c minus 14 is equal to 0. Any factorization? Cosine theta is equal to negative 2/3, you're saying. So c is equal, c plus 2/3 must be the same. That is 3c plus 2. So for 3c plus 2, like this is 3 times of 6, you would want 12, I guess. So 18c square plus 12c. Wait, what? Is that right or not? Must be 12. Then minus 3c minus 14. No, okay, that's not 14. Not what we want. 14. Ooh. No, not nice. That must be factor for this thing, right? Is this a factor? What's like 4 upon 9 cancels, you get 8. 8 plus, what's this? 8 plus, oh, it's negative, sorry. It's gonna be, but that's what I'm doing, right? I want to make it negative, and yeah, exactly. Huh. That's negative over there. It's supposed to be just negative 2/3 of this as like negative. Yep, it won't work. It won't work like that. Must have gone wrong somewhere. Where did I go wrong? Let's see right there, of course. When I get a squared and b squared, right? No, I can't possibly be correct right here. It's not correct. Okay, then. Let's put everything in there and then that c goes over there, so it's minus 2bc squared. Okay, it will be minus d times c. Yeah, sure, that's correct. And then 2a, then minus 2b is like 2a. So a minus b, and then you got c squared, and then no, it's correct. It's minus a. That I thought it would be plus a, no, it's not. And okay, that's where it's supposed to be negative. That's where I went wrong. It's supposed to be negative right there. Then this is also negative. And that's also negative. Now let's do it. 18c squared plus 12c minus, it's got to be 12 plus 9, which is 21 minus 21c minus 14 is equal to 0. And we just want like 3c plus 2. So 3c plus 2, and then we got 6 and minus 7c is equal to 0. So either c would be just negative 2/3 or c is equal to 6/7. But wait, both of these actually work, right? So that's one possibility. You could also have this thing. Oh, maybe like 2 theta won't work if it's 6/7 or something. But theta is already negative. It has to be like uh, it must work in this case as well. What's stopping it? No, it can work for sure, right? Yeah, right. So it's actually having two values. It's either negative 2/3 or it's uh or it's 6/7, right? Okay, next question. Yeah, that has to be correct. What else? I didn't make any mistakes, did I? Nope. Next question. Eighth. A normal chord to this ellipse makes angle 45 degrees with the x-axis. Okay. Prove that the square of the length is equal to this. On chord to this ellipse makes angle 45 degrees with the x-axis. So slope 1 basically. It's a normal chord, huh? Fine. Prove that the square of its length is equal to this. Okay. Square of its length. That is equal to 32 whole power 4 e power 4. Fine, let's do this thing. No big deal. Just have to do that. So the thing is like, why? Maybe that's not the best way to do it. It is normal chord. Doesn't say anything about where it's passing through or anything like that. Square of its length. It's already complicated at that point. You can figure out the midpoint. Yeah, sure. But in you want to figure out the square of the length, which is, it's a hard thing to do actually. Okay, let's do it. We'll see what we have. Okay, so how do you get the normal chord? Oh, okay. I think it's important that it's a normal chord, right? Not just any chord, it's a normal chord. And the square of length. It's going to be like that. I really think maybe if I just deform it back to a circle and then do something with that. So yeah, that chord will just be okay. And the tangent is at m equal to -1. That will also change, of course, but it will still be a tangent. That's the main thing. So you can just figure out, hey, wait, what am I looking for? I can directly figure out the eccentric angle. Yeah, okay, one of these eccentric angles is no, basically. Right. And then the other guys, okay, it might not be that difficult because once you know this thing and hey, hey, wait a second. Okay, I know how to do this. Yes, I know how to do this. Okay, let's do it. So what's the normal? It's like x a upon no, yeah, x a upon cosine minus y b upon sine is equal to a square minus b squared. What's the slope? The slope is, so you gotta do that. It's supposed to be s upon c, and then that times of a upon b, I guess. Yeah. So tan theta times a upon b, and that has to be equal to 1. So tan theta is equal to b upon a, basically. Right. So now I know what theta is. It's times of b upon a. Cool. And okay, so still it's hard to figure out what that point is actually. It's like a cosine theta and all that stuff. Cosine theta is already bad. Just leave it like that. Don't touch it anymore. Right. So now just got a cosine theta and b sine theta as the point. And then this is making 45 degrees. So we'll just add a vector. So we'll add a vector, say r comma r. Or instead, let's just say r times 1 comma 1 upon square root 2. So then r will be the distance, of course. And we just want, for what value of r will this once again lie on the equation of the ellipse, right? Yeah, exactly. So it's gonna be hard. That will be dependent on theta throughout. What other choice do we have? Okay, you know what? We'll not do this. We'll just do r comma r, and yeah. So after all, we will figure out what this vector is, what's the length of this vector basically, and we'll see what we get. So AC plus R, that thing squared is supposed to be a squared c squared plus 2ACR plus r squared, all of that upon a squared, and then plus bs upon bs plus r squared. Like once again, same stuff. B squared sine squared plus 2bsr plus r squared, all of that upon b squared. That has to be equal to 1. So what value of r works? Of course, like 0 should work, I guess. Okay, this is like r squared times 1 upon a square plus 1 upon b square. Then for r, you will just have, say 2r actually, 2r, and then you gotta have cosine upon a plus sine upon b, and this will cancel out. So it's 1 cancels, is equal to 0, right? So either r is 0, or the other choice would just be r is equal to negative times c upon a plus sine upon b upon 1 upon a square plus 1 upon b square, right? So we just want the magnitude of that, and instead of this, actually want this thing upon square root 2. There we go. That's the length. That's the length of the chord. Sure. So notice this is a constant. We just care about what this thing is. Still not nice. Yeah, okay. So c upon a and s upon b, that's equal to 1. Wait, what? Shit, c upon a is equal to s upon b, right? Yeah, well, what is c? C is just, okay. So it's supposed to be b and a like that. So that's theta square root of a square plus b square, right? So a upon all that stuff, that's gonna be c. Then that upon a is, oh wow, nice. So 1 upon square root 2, this goes up, a square b square upon a square plus b square, and then this whole thing is supposed to be 1 upon so actually 2 upon square root of a square plus b square, right? Yes. Oh, it should be negative 2 right there. Sorry. Because that went like that, right? Okay, cool. So actually supposed to be 4 upon that. Makes sense, I guess. And we just have to prove that this is a thing. Well, it doesn't look like that. Oh, we want the square of it. Fine. So this thing is just going to be 2 square root 2. Square that, just get... Wait, you should get 32, not this. Right? Yeah, well, what went wrong? What just went wrong over there? You got r. We should just have r upon square root 2. That will be the thing. Oh, no, sorry. R times square root 2 is the length of the vector, right? We should have this times square root. Okay, that's supposed to be 4 square root in that case. Oh, yeah. So then it's 32 a power 4 b power 4 upon a square plus b square power 3, right? Which is what we want. Yeah, exactly. Okay, next question. This is done. 9th. If x1, y1, x2, y2 are 2 points on the ellipse, the tangents at which meet, I think that means which meet in h comma k, and the normals in p PQ. Okay. Okay, so at that refers to the to these 2 points. So these are 2 points such that the tangents at them meet in h comma k and normals in p comma q. Prove that. So a square p is equal to, okay, fine, fine, fine. This is essentially ah, okay. It's hard, I guess, because x1 x2 ah, interesting. Isn't that basically asking what h comma k and p comma q are, right? Yeah. But x cosine theta. Okay, no. Instead of that, we just use this thing x1 upon a square plus y1 upon b square is equal to 1, right? That's the tangent. So x1, y1, and x2, y2 are the equations of that, whatever. Wait, isn't that just the chord of? Oh yeah, sure. Okay, okay, that makes sense. It is the chord of, like, okay, it is the point whose chord of contact passes through these two, basically. Right, right, right. Oh, okay. So what's the line between these two? It's supposed to be, so you might as well just say, okay, y minus of y mid, which is uh, y1 plus y2 upon 2, and then upon x1, so x1 is like x1 plus x2 upon 2. That would just be equal to, this is crazy. Why is that even? Yeah, right. It's gonna give us some stuff like that, but then it's not very direct. I mean, you could have some other point x1, y1 doing the same thing, right? So, not very nice actually. Some other thing that, yeah, like what else can we do? I guess we just have to figure out the equation. So yeah, the solution to these two systems, these two equations, right? Yeah. We got x2 upon a squared plus y2 upon b squared is equal to 1. It's not nice, not nice. So yeah, okay, you want a squared p is equal to e squared h x1 x2. Why? Why do you want? Why is that the thing? A square p. Hmm. Why is that this a square p square? I don't get. Okay, p comma q is just the point where it's like normal and stuff. Huh. Think about it. What I'm thinking is that you got a circle passing through h comma k and p comma q, and then you have these two on that, something like that, right? This is not nice. To intersect like that or something. Ah, just have to solve this. There's no other way. Is there? I don't think there is. And then it was like k. Wait, okay, why is this only involving the x coordinate stuff? Why is this not involving the y coordinate things? Uh, that must be because, yeah, okay, okay. It has to be because of that whole thing going on, right? What else could be the reason? Or maybe like you have some kind of equation in x, right? Yeah, that would be another thing. Uh, Wait, okay, I think I got it. I got what they did. So x minus h times x minus. So what was the thing? Sorry, the other guy versus p. So x minus p plus y minus h. Sorry, y minus k, and then x minus q. That would be the circle, right? And then x1, y1, x2, y2 are points on this circle, basically. Okay, nice. And we know that x square. Oh yeah, okay, that's something we can do as well. Think, think. These two are on the circle. Sure. And then you can always put x square as this thing or something like that. kx square minus h plus p times x plus ph, then y square minus 3 plus q times, no, it should be y. So y and then plus kq is equal to 0. That's the equation of the circle. Like what you're saying, like x1, y1, x2, y2 are points on that. But then for both of them, this is supposed to be true. So I just want to write it using that somehow. It's like, okay, b square x, sorry, yeah, like b square x square plus a square y square equal to 1. So what if I multiply this whole thing by a square b square, or divided this whole thing by a square b square, right? Yeah, okay. Okay, that would work. Would work, sure. It's gonna cancel out these guys. Actually, not cancel out. No, no, no. That's not what it. That's not what it's doing. It's doing something else actually. Okay, now my brain is not working. What do we do? How do we proceed here? Uh, why is this only in h? Sorry, it's only in x coordinates, nothing else. Must be something special about the x coordinates, and this is completely in y coordinates. There's no x coordinate involved over here. Why is that the case? Look, both are very much of the same kind of form. And what's k? What's k over here? Oh, that's k. Okay, so k y1 y2 k square whatever. Why is that the case? Has to be some other way than just doing algebra. There must be some other way, right? Or a circle and then 2 points on this circle. How is that even helpful? Uh, these 2 points are on this thing as well as that thing. Maybe that's important, right? Yeah, well, okay, that linear term, that's not helping. That's not helping. Mhm. You will get some more equations, right? So actually, no, you will get there's like two equations, not more. Okay, so it's two equations in x, y, and stuff like that. Okay, so fine. It's not circle like that. So the thing is, it's tangent to that. That's important. How can you just, I mean, like ignore it? No, it's very important. You have to use that fact, right? Huh? Okay, just figure out the thing. I don't think it's gonna have a solution. Okay, just do it. Pathetic. Fine, figure out what h is. Just multiply by x2 over here. It's supposed to be h x1 x2 plus that goes over here. It's like k y1. Oh, okay, we don't want to eliminate that. Instead, multiply by y2 other h x1 y2. But then it involves this y2 term that we don't want. Whatever. K y1 y2 upon b square is equal to 1, and then same stuff over here, right? In the end, oh, it's equal to y2 by the way. So in the end, what you want is like h times of, sorry, h upon a square, and then times x1 y2 minus x2 y1 upon a square. That has to be equal to so y2 minus x y1, right? Sorry, yeah, that's better. It's still just horrific, not helping at all. I think I need to break. I need a break. Okay, so I'll see you guys in the next video. Fine.